Today we're going to introduce a new circuit element, the operational amplifier. The operational amplifier is an interesting element because it's really not a circuit element at all. It's an integrated circuit. So it's a whole circuit in and of itself that contains multiple resistors and capacitors and things like that. But analyzing it from the interior of the IC is actually extraordinarily difficult. We are going to look at it from a macro scale from the outside of the op amp, and we'll actually observe that it behaves using a couple of very simple rules that we can use to do circuit analysis on circuits containing op amps. So the schematic symbol for an op amp is a triangle, like so, and you'll see a plus sign and a minus sign on the wide side of the op amp, where the plus sign corresponds to what's called the non-inverting input, and the minus sign corresponds to the inverting input. There's a third terminal, which is our output terminal. And these are the three terminals that we are largely going to concern ourselves with for our circuit analysis. Now, there are actually potentially four other terminals that could be on an op amp, and we're going to talk about two of them specifically. I'm putting them in a different color to let you know that they're optional. Optional in as much as they don't in any way, shape, or form influence our circuit analysis, but without these pins included, the operational amplifier will not actually behave like it's supposed to. And these are the power supply terminals. So we're going to have a VCC plus, where positive power will be supplied, and VCC minus, where negative power or negative voltage will be supplied. The op amp is an example of an active circuit, so it requires external power to behave in a particular way. So resistors, capacitors, and inductors are all passive elements because they don't require external power to exhibit their specific resistance, capacitance, or inductance, but an op amp needs power to operate correctly. There's a lot of nuance in these power supply pins. As far as how the output voltages of the op amp can behave. But for the intents and purposes of circuits 1, we are just going to assume that the biasing voltages are high enough to cause the op amp to behave normally. All right, so there are two very specific rules on how an op amp behaves, specifically an ideal op amp. Rule number 1 is that there is no potential difference between the input terminals. So what that means is that if we apply a voltage, let's call it V minus, at the inverting input terminal, this voltage V plus, the voltage at the non-inverting input terminal, has to be the same voltage. Another way to describe this is that there is a 0 volt potential difference between these two terminals. Now, technically, this is only true whenever we have a negative feedback circuit. And I'll explain what that means in just a moment when we work an example problem. Now, rule number 2 is there can be no current flowing into or out of the input terminals. So that means I could have a current, which I'll call I plus, trying to flow into the input terminal. And for an ideal op amp, this current is, by definition, 0 amps. And the same thing could be said for a current I minus trying to flow into the inverting input terminal. Now, this rule does not say anything about the current that can flow into or out of the output terminal. And for our intents and purposes, any current that needs to flow into or out of the output terminal can. These rules come from some characteristics of operational amplifiers. They are beyond the scope of this class. That being said, if you're interested in looking at them, I have several lectures on operational amplifiers for my ELEN 223 class that you guys could look at if you wanted to get more information. So let's analyze a simple example circuit using these two rules. So I'm going to have my All right, so this is our example circuit. Now, a few minutes ago, I mentioned something called negative feedback, and specifically that this particular rule, rule number 1, is only valid for negative feedback circuits. Well, this circuit exhibits negative feedback because there is a current path connecting the negative or inverting input terminal to the output terminal. So this is what's called a feedback loop. And because it's between the negative or inverting terminal and the output, it is a negative feedback loop. If instead we saw a feedback loop between the non-inverting terminal and the output, that would be what's called a positive feedback loop. All of the circuits that we're going to analyze in Circuits 1 contain negative feedback loops so that we can apply these ideal op-amp rules. All right, so our goal in this example is to determine this output voltage, which is measured with respect to ground. So it is the same as the voltage drop over this 1 kilo ohm resistor. So if we apply our ideal op-amp rules, we can observe a couple of things. So first, we know that this current that I'm drawing in red must be 0 amps, and this other current that I'm drawing in red must be 0 amps. And this voltage drop between our two input terminals must be 0 volts. So we have applied our two ideal op-amp rules. So our first step is going to be to determine our nodal voltage at the non-inverting input terminal. So that nodal voltage I'm going to call as V+, and this is the voltage drop measured at this terminal with respect to ground. So we know that 0 amps of current is flowing into our non-inverting input terminal, which means 0 amps of current must be flowing through our 2 kilo ohm resistor. Therefore, there's no voltage drop over that 2 kilo ohm resistor. And so the voltage present at the non-inverting terminal must be 5 volts, which is being supplied by this voltage source. Excuse me. So to be clear, due to op-amp rule number 2, whatever voltage we have at this node must be passed on to this node because there's no voltage drop over that resistor. Now we know that the nodal voltage at the inverting input terminal has to be the same as the nodal voltage at the non-inverting input terminal due to rule number 1. So if there's 5 volts here, there must be 5 volts here as well. And that 5 volts, again, is measured with respect to ground. Now we could observe that there is no current flowing through this 5 kilo ohm resistor, so there's no voltage drop over it. There's no current flowing through this 10 kilo ohm resistor because that would involve still having a current flow into or out of this inverting input terminal. And so these, the 5 kilo ohm resistor and the 10 kilo ohm resistor aren't really doing anything because there's no voltage drop over either of them. So from this, if we developed a Kirchhoff's voltage law equation around this loop. So I'm starting here. I see the negative polarity terminal, the 5 volt source, a 0 volt drop, like so, where I'm starting at ground and I'm ending at ground. I would see that negative 5 volts, the voltage drop over this source, plus 0 volts, the potential difference over these terminals, plus 4 volts, plus V out, is equal to 0 volts. And I could rearrange this to find that V out is then equal to 1 volt. And we have successfully analyzed actually a kind of difficult looking op-amp circuit. So applying these two rules is all that you will need, as well as using basic nodal analysis techniques. Let's see. Our next lecture is going to be using these two ideal op-amp rules to analyze a lot of different op-amp circuits that are commonly used in practice. So we'll get a lot of practice using these op-amp rules throughout these examples that I'm going to give you, as well as your homework and things like that. If you have any questions on how to apply the ideal op-amp rules, or you'd like more example problems, please let me know. Thanks for watching.